Thanks, Jalil. Okay, so just a super brief reminder of what I told you yesterday. So the first lecture was about gradient descent and the first miracle of gradient descent, which is its robustness even to adversarial noise. So that was lecture 1. In lecture 2, I told you about the mirror descent flow. And I did the second miracle, which was the Bregman divergence analysis. So when you take the derivative, you have something very simple in terms of the gradients. What I'm going to tell you today is more applications of this second miracle and also a third miracle. And at the end of chapter 2, I wanted to go from the mirror descent flow to the discretized mirror descent algorithm, which I still haven't really written on the board. I will do that tomorrow. It's slightly more technical to do the discretization. Today, we're going to do everything in continuous time. We will have an application in discrete time, but it's nicer to stay in continuous time. So discrete time will come tomorrow. Okay, so chapter 3 is going to be the metrical task system problem, metrical task systems, and the third miracle. Okay, so I will start by defining what is MTS for metrical task system. So MTS. So let X be a finite metric space. Okay, so if you like, you can think it's just a graph, a finite graph with weights on the edges. Now we're going to play a sequential game, a discrete time sequential game. At every time step, so the player maintains a state, which we're going to denote rho t. So at time step t, the state is rho t in X. Okay, so think of X, your finite metric space, as your state space. So you can be in any state at a given time. Now, at time t plus 1, the player receives a task function. So what is a task? So you have this state space, and you have to complete this task. And the encoding of the task is that to complete this task in a given state is going to take you a certain amount of time. So you can think that the task is a cost function. So a task function, which is a cost ct from x to r plus. Okay, so in every state, it's going to tell you how long it takes to complete this task in this state. And we are time step t plus 1. So right now, you're in this state rho t. And maybe if you stay in that state, it's going to take a very, very long time to complete the task. Okay, so what you might want to do is that you might want to update the state to get to a state where the completion time is going to be smaller. So receive a task function and move to rho t plus 1. And now you're going to pay the movement cost. There will be a movement cost to update your state from rho t to rho t plus 1. And there will be what's called the service cost, which is ct plus 1 evaluated at rho t plus 1. Okay, so we have a movement cost, which is the distance from rho t to rho t plus 1. And we have a service cost, which is ct plus 1 of rho t plus 1. Okay, so this model was introduced by Borodin, Lineal, and Sachs at the end of the 80s, and the journal paper is from 92. Okay. So maybe it's not completely obvious, but this problem actually models like hundreds of applications. So I will give you just a couple of them, and these are real applications. So, yeah.
Just to clarify, you evaluate the cost function of the new state.
Yes.
After you paid the service.
Absolutely.
After you paid the movement cost.
Yes. So for instance, it could very well be that the cost is actually infinite in some part of the state space. You just simply cannot complete, this task in that state. Okay, so some applications, I will just give you, just to give some context. So some applications. One of them, which I really like, is, it's a class of application, self-adjusting data structures. So you can think that your state space is basically the description of your data structure. And as you get more and more, problems that you have to solve with your data structure, you might realize, oh, it was better actually to change, this parameter or that parameter of the data structure. So you want to update it as you go. So you have this learning process on top of the data structure selection. So just to be concrete, an example is imagine that X is a set of permutation, okay, on L elements. And the cost functions, so your data structure is just a permutation, okay? You have n items, and what you choose is a permutation of those items. And if you have a certain permutation, I don't know, maybe 3, 2, 4, 1. And if now element 2 comes, element 2 comes, and you're looking in your index, where is element 2? So this is going to take you time 2. If 1 comes, then you have to go through 3, 2, 4, 1. Okay, it's going to take you time 4. And if you keep getting 1s and 1s again and again, maybe you want to put 1 in front. Okay, but this will cost you something. You have some notion of distance on the set of permutation. Okay, did that example make sense? Or do you want me to make it? Yeah, makes sense? Great. So that's one example. But you can imagine an infinite amount of examples here. Another one is power management. Okay, so just I want to bring your attention to the fact that here, the size of the state space, although it's finite, it's exponential in the parameter of interest. Okay, just to clarify. So power management, here is a very simple example. You have your computer, and it has 3 states. It has the state on, so let's say on. It has the state sleep, and it has the state off. And you see it's a line like this, the metric space. And this distance is much bigger. So if I want to bring my computer from off to sleep, let's say, or to on directly, it's going to take some big amount of energy. Whereas to move from on to sleep, it's a much smaller amount of energy. Okay, so this metric space represents the structure of the metric, represents the amount of energy consumptions. And now I can have 2 tasks. So task 1, so maybe let me write it like this. So task 1, what is going to be the cost of task 1? Is going to be, task 1 is I want to use my computer. Okay, so it's 0 here, it's infinite here, and it's infinite here. I have to be on, that's it. I want to use my computer. And task 2 is that I'm not using my computer. Then if it's on, maybe my power consumption goes at a rate of 1 or some parameter. If it's in sleep, it's some epsilon. And if it's off, it's 0. Okay, so you see, if I see task 2 over and over again, at some point I want to move to the off state. But then it's going to, maybe I get hit with task 1, and it's going to take me a lot of energy to go back. Another application is that this problem is strictly more general than prediction with expert advice that we saw last time. Okay, so what's the big difference with prediction with expert advice? So let's imagine that the metric space right now is trivial, so everything is at distance 1 of each other. The big difference is that in prediction with expert advice, I had to take a decision before seeing the cost function. You remember, I take a decision, then I see how well I was doing. Whereas here, I see the cost function first. But notice that if I don't move, then being evaluated on the next cost function or the current one, it's the same thing. I didn't move. I played the same point. Okay, so the cost that I get when I'm evaluated on the next cost function is upper bounded by the cost when I'm evaluated on the current cost function plus the movement cost. Okay, so this is literally just strictly more general. Okay, so in particular, what I'm going to do in this lecture is that I'm going to show to you how to use mirror descent for this framework. And there we will really like to have this flexibility of choosing the mirror map or the Riemannian structure on the manifold because we will allow it to match the metric structure. Okay, so that's going to be the flexibility that we're looking for. In particular, I will derive completely from first principle the entropy, and we'll see why the entropy arises here. Okay, any question on the model and what we're going to do with it? Okay, So the type of guarantees that we're going to look at, so type of guarantees. So we're going to have something very explicit, but people in the literature are very interested in what's called competitive ratio, which I'm going to denote like this. It's alg. So by alg, what I mean is I have a certain algorithm which is running for capital T time step, and it has paid a certain service cost and a certain movement cost. And what I want to compare it is to opt, which is the best I could have done in hindsight. So given all of this sequence of requests, what was the best sequence of states that I could have visited? Okay, so think, for instance, about my data structure example with the set of permutation. If I get hit with 1 all the time, then the omniscient algorithm would move 1 in the first place immediately. But then I could have something where I have to move 1 in the first place, and then I have a bunch of 2s, and then followed by a bunch of 3s, followed by a bunch of 2s. So then the optimal algorithm exactly knows that when a streak of 3s start, it needs to bring the 3 before the 2. Okay, so it kind of sees into the future. So the big conjecture in that field, so this is in the field of online algorithms, this is the central model, which generalizes everything. And the conjecture is that for any metric space of size n, there exists an order log n competitive algorithm. Okay, so this conjecture is still open, and that's one reason why I'm talking about it. It would be very interesting to solve it. So what is this? Okay, so what is this log n? So the key insight, or the one reason why I started looking at this question is, where does this log n come from? So far, on the first day, you saw 2 log n, or log d. One was in Joel's course, which was this coming from this union bound, for concentration on random matrices. And the other one was the log n in exponential weights in the regret bound square root T log n. So those 2 log n's are actually the same. Okay, so for instance, you can reprove what Joel was doing with mirror descents. That's very nice. I highly recommend looking at the paper by Sasha Racklin and Kartik Sridharan, who uses mirror descent with the quantum entropy to reprove those matrix concentration results. So anyway, the story is that these 2 log n, they are like entropic log n. And the question is this log n also an entropic log n? Is this the same log n as in the square root T log n? Okay, and we still don't know the answer. It goes beyond what was seen in the first lecture because there is this very general metric space in the picture. But what we're going to see today, so over the course of those 2 lectures, I'm going to prove for you the following result. So this was myself, Michael Cohen, James Lee, and Yintat Lee last year. What we establish is O of log squared n. Okay, so again, remember this log n. I mean, in some example, it's really a log n, where n is really the parameter of interest. But in many examples, n is exponential in the actual parameter of interest. So the log n is really the parameter of interest, if you want, in those combinatorial settings. Okay, and you will see exactly where does this extra log n come from, and there is a very cute open problem for how to remove it. Okay, but before we get into mirror descent and this type of result, let's do some warm-up. So warm-up. Deterministic strategies. So one thing I was a bit imprecise here. We're going to look at randomized strategies, and we're going to look at this quantity in expectation. Okay? But you can also ask the question for deterministic algorithm, and for deterministic algorithm, it was fully resolved in the Bordin-Lignal-Sachs paper. Let's just do it on uniform metric, just so that you get a feel for what's happening on uniform metric. Okay, so here is a super simple algorithm. Uniform metric just means all the distances are 1. Okay?
Sorry.
Yeah?
Is there no lower bound for this conjecture?
Yes. It's extremely interesting also. So here is the lower bound. For any x, omega log n over log n is necessary. Okay, and in fact, this log n, so removing log factors, or log factors in this case, even though it's not striking in terms of the result itself, it can lead to really dramatic new insight. And here, it's really a case where, okay, it's just a log n, but there is really something fundamental that we don't understand about the problem. And it will make more sense later in the second lecture, I will explain what's going on in this lower bound. Yeah?
Sorry? Can you explain what means a competitive algorithm?
What means what?
To have a competitive algorithm.
A complexity algorithm? Competitive, sorry. Sorry, yeah, of course. Competitive just means that the competitive ratio is bounded by this. Alpha competitive means that alg is smaller than alpha times opt plus a constant. Yeah, sorry. Thanks. Okay. So it turns out that for deterministic, the best you can do is not log n, but for the n. Okay, which is really, really bad. Think about this example of the permutation. So basically, deterministic algorithm cannot really work, and it makes sense. I mean, imagine this example. If I have a deterministic algorithm and I have to have a worst case guarantee, then you can think there is an adversary that knows what I'm doing. So whenever I turn it off, it's like, oh no, actually I want to use it. Okay, so you can imagine that you cannot have really good guarantees for deterministic algorithms. But let's just see it anyway. So here is an algorithm. So stay in a state until it accumulates a cost of 1. Okay, so once it has accumulated the cost of 1, we're like, okay, maybe there was a better option out there. So what you do is then mark the state. Okay, you're like, okay, I know this state was bad. Okay, it has accumulated the cost of 1. You can think like if the optimal algorithm was staying in that state, right now it has already paid 1. So either it's not there or it has paid the cost of 1. And if later on it moves there, it also pays the cost of 1. So no matter what, I know that I can leave that state for the moment and move to an unmarked state. Okay, the algorithm is clear. So just whenever a state gets a cost of 1, I mark it and then I move somewhere else. At some point, I'm going to mark everything. And when I mark everything, I just flush all the marks. I say, okay, now I know at that point, opt must have paid 1. So once I have marked everything, I know that opt must have paid 1. But how much did I pay? I paid at most 1 of service cost per state, and at most 1 movement cost per state. So in total, I paid at most 2n, and opt paid 1. So I'm competitive of 2n. Okay, so once everything is marked, I paid less than 2n, and opt paid at least 1. So I'm 2n competitive. Okay? Is it clear?
Can I always move to any state I want?
Yeah. All the states are open to you. It's just that, okay, in this case, all the states are at distance 1, but in more complicated cases, some states could be very far away.
Here it doesn't matter where
Here it doesn't matter, yeah, exactly.
So when you say that you wait till you pay 1, you mean it could be that the cost is greater than 1 at this particular instance.
Then I move out. You remember, I pay at the location at which I land.
So you look at what it's about to cost you and only if it's greater than 1.
Exactly, that's right. Yeah, I mean, of course, like I could write equations to formalize this, and then we would clarify this point. But you get the spirit.
And then you redo it again?
Yes, once everything. Yes, that's right. Once I remove all the marks, then I start from fresh. Exactly. Okay, and this is clearly best that you can do. Okay, so this is O of n. Now the omega n reasoning, I don't know, it's just, you're somewhere, okay, I hit you. I put an infinite cost wherever you are. Okay, so the cost function, Ct, is always, Ct plus 1 of rho is always going to be infinity at the location rho t. Okay, I just kick you out all the time from the location where you are. So now I kick you out from this one, then from that one, etc. The point is that opt can see into the future. So it can move to the location which is going to be the requested the furthest away in time, which is at least n time step away. So over n time step, opt pays less than 1, and I pay n. Okay, so over n time steps, I pay n, and opt pays less than 1. So omega n competitive. Okay? Yes?
Just to be clear, so the choice of the constant 1 is arbitrary between 2
Where is there a constant 1?
for the cost.
Here it's infinite.
Yeah, but if you stay until the cost is above 1,
Ah, sure, yeah. Whatever, yes, yeah. I mean, it's going to affect these two, but yes. Yeah. Yes, absolutely. Okay. So was this clear? Just to get the stage. Okay, so now let's see what happens for randomized. Okay, for uniform spaces. So see here, I just said move to an unmarked state, any one of them. So now if I'm randomized, I'm just going to move to a random unmarked state. Okay, so move to a random unmarked state. Now what the point is that, imagine I have n states left right now. I'm in some random state. What's the probability that this is actually the first state that gets a cost of 1? It's 1 over n. I mean, there is some state which is going to get a cost of 1, and there is a probability 1 over n that I'm in that state. And if I'm not in that state, now there is one state that I removed without doing anything. Okay, so the equation is going to be if I denote f of n to be the expected movement when n states are unmarked, then I have the recurrence relation that f of n is 1 over n plus f of n minus 1. So again, the only reasoning that I have is just I wait until one location accumulates a cost of 1. When this location accumulates a cost of 1, I'm going to mark it. I'm going to say, okay, I know opt cannot be there. There was a probability 1 over n that I was in that state. And if I'm in that state, then I need to move, so I get a cost of 1 over n. And if I'm not in that state, then I have just not moved and reduced to n minus 1 state. Okay, so this will give me f of n is log n. I mean, up to a constant. Okay, so my movement to achieve the same thing as before is only log n. So my service cost and my movement are the same in that algorithm. So I only get log n movement. Okay, as a very, very simple variation of this. Okay, what about the lower bound? So the lower bound, what the whole point of a randomized algorithm is that if I think about the cost sequence as an adversary, the adversary doesn't know where I am. Okay, right now I'm randomized at a random location, so it doesn't know where I am, so it cannot hit me, surgically like this in a very precise location. So what the best he can do is to hit a random location. He has no idea where I am, so he just hits a random location. If he hits a random location, very good. So right now the cost is going to be plus infinity at a random location. That's the hard sequence. So what happens? Again, what is my cost? So alg's cost over n time is 1 in expectation. Right? I hit random location, so if I do like n of them, let me see, what am I saying? Right, just because, right, if I do n of them, then at some point I'm going to hit that one where alg is. But what about opt? Now you have the coupon collector phenomenon that kicks in, which is how many requests is it going to take for me to hit the whole state space, all the location. It takes n log n. But it takes n log n steps to cover x, to hit all the location. Right? So opt pays 1 only every n log n time step. I pay 1 every n step, so that's a log n gap between the two. Okay, so that's the lower bound of omega log n. That implies the omega log n for randomized. Okay. So this type of arguments has been pushed to death in the 80s and 90s, and people were really working on this type of combinatorial arguments, and they were hitting a wall just for the very next metric space, which is not a uniform space. So what is a uniform space? Uniform space, you can think there is like a root. We're going to think a lot about trees. And then you have all the leaves here. Okay, so this is 1, 2, up to n. And let's say if I want to have a metric 1, all the edges have length 1/2. Okay, this is my uniform space. So we understood everything for uniform spaces like this. But the next one is just slightly more complicated. It's when you have weights on the edges. W1, W2, up to Wn. And this is already much more interesting because, for instance, it applies to states like to state space like this, to power management type problems, where you have certain states which are much further away than the other one. Okay, so it's really the weighted star case opens up a whole other set of application compared to the uniform metric. The uniform metric covers prediction with expert advice and other interesting things, but not this. Okay, so now I'm going to move on to the weighted stars and explain how to use mirror descent to solve this problem. Is there any question on this? Right, and for instance, coming back to the lower bound question, we don't know how to prove a log n lower bound for weighted stars. By this I mean, for any weighted, like given a weighted star, prove a log n lower bound. Of course, for some weighted stars, we know a log n lower bounds, like for the weighted star which is uniform. And this is, you see, it's really about a kind of weighted coupon collector. So it seems extremely basic, but we don't know how to do it. So how we do get lower bounds for weighted stars is crazy. It's using what's called metric Ramsey theory, which I'm going to tell you about in the next lecture. So you know, Ramsey theory, it's about finding, you know, some kind of that in any structure of a certain type, you must have a certain substructure. So for instance, metric Ramsey means that in any metric space, you must have like a big tree in it, something like this, or a big uniform space. These are metric Ramsey type questions. And we know that in any metric space, there exists a big, what's called HST, hierarchically separated tree, which we're going to see in the next lecture. And so what you do is that you apply these very general math statements about metric Ramsey to the weighted star, and then you prove a lower bound on HSTs, which seems crazy, but that's the best argument we know. Okay, so now let's go back to mirror descent and see how it fits in here. How am I doing on time? Yeah. Okay, so right. So this was 1, 2. Beyond uniform spaces. Weighted stars. Okay, so the first thing I'm going to do is to move in continuous time to make it amenable to the continuous time gradient descent or mirror descent. So continuous time problem. It's just that instead of Ct for t in n, we have C of t for t in R plus. Okay, so you just now, you have a continuous time pass of cost functions, and you can make decisions in continuous time. Okay, so at some time you decide to move, at some times you decide not to move.
But the move is instant.
The move is instantaneous. Of course, in principle, you have more power. I mean, how do you turn a discrete time problem into a continuous time problem? There are many ways to do it, and in principle, maybe it could be easier to solve the problem in continuous time. So it's not clear that the continuous time version of the problem is as hard as the discrete time. Okay, so let me just prove this to you. So lemma, continuous time guarantees transfer to discrete time guarantees. Okay, it's very simple. Although the literature is full of wrong proofs of this. Maybe I shouldn't say that on camera, but so anyway, let's do a proof. So what I'm going to do is that so I have a discrete time problem, and I have a continuous time algorithm that I can apply to any continuous time cost function. So what I'm going to do is that I'm going to tell you a procedure to turn a discrete time cost into a continuous time cost. Then I apply my continuous time algorithm, and I'm going to tell you how to transfer this continuous time algorithm into a discrete time algorithm. Okay, very good. So the transformation from Ct to C of t is a water filling transformation. So again, I don't want to write, I really don't like discrete mass equations, so I'm just giving you in words, and then, you know, when we do analysis, I can write the equations. So here is the thing. So you have a cost like this. Okay, so this is my discrete time cost function, right? So this is state 1, 2, 3, etc. You have these different costs. And in continuous time, what I'm going to do is that, you know, I just give a cost of 1 at a rate of 1 to everybody until, you know, I reach this level, let's say like this. And now I drop, now those guys, they don't get cost anymore. Now only those states get a cost until I reach here. Now it's only those two states that get a cost, etc. So this is my discrete time to continuous time. It's this water filling process. Okay? Now from, let's say, rho of t to rho t. Okay, so now I did this description. Now I run my continuous time algorithm. I get a continuous time description of a state. Okay, so maybe I move at various points in time, etc. Now I need to tell you a discrete time movement. So what I'm going to do is simply to rho t, which is the smallest cost state visited by the continuous time algorithm. Okay, so in continuous time, my algorithm is doing something. It's moving from state to state. And no, maybe it never visits that one, it never visits that one, but it visits this and this. Okay, so if it visits those two states, then what I'm going to do in discrete time is that I'm going to straight move to this one. The point is, the service cost of the discrete time algorithm is smaller than the service cost of the continuous time algorithm, because of the water filling process. You know, the algorithm, the continuous time algorithm, has only visited states which had at least this amount of cost. So they suffered that amount of cost during the whole process. And and the movement cost is certainly, movement cost of the discrete time is certainly smaller than the movement cost of the continuous time. Because the continuous time, it did move there. So I'm just mimicking that move. And maybe I'm ignoring a bunch of other moves. So my service cost in continuous time, or in discrete time, is smaller, and my movement cost in discrete time is smaller. But opt in continuous time is certainly smaller than opt in discrete time. I mean, that's the whole issue of the model, is that in continuous time I have more power. So opt in continuous time, it can do more than opt in discrete time. Right? It can certainly do exactly the same as discrete time, or maybe more. Okay? So if I have a guarantee in continuous time, if my service cost plus movement cost in continuous time is less than alpha times my opt in continuous time, then I know the same thing for the discrete time, because the discrete time, service cost is bounded by the continuous time service cost, which is bounded by opt continuous time, which is bounded by opt discrete time. Anyway, it's very simple, but maybe a bit confusing sometimes. Okay, so now we are in continuous time. The next move is to move in continuous space, because we want to use mirror descent. Okay, so continuous space. Okay, the continuous space problem, we already did it for prediction with expert advice. It's just, instead of thinking of a random state, we're going to think of the distribution of the state. Okay, so instead of rho t in X, we maintain xt in the simplex, in delta n, okay, which is just a probability distribution. And now the cost, the discrete movement cost here corresponds to a transport distance in terms of the probability distribution, or a Wasserstein distance. So the distance between rho t and rho t plus 1, this is going to correspond to W1 between xt and xt plus 1. Okay, remember W1, the Wasserstein distance, is just the best coupling that I can do in terms of the distance in the metric space. So this is the infimum over all pairs of random variable x, y, such that x is distributed as xt, y is distributed as xt plus 1, of the expectation of the distance between x and y. Okay? So if I control the movement cost in terms of the Wasserstein distance, I get a discrete time, like an integral algorithm, by just sampling through this optimal coupling. Okay, what does it mean? It just means, imagine that right now I have my continuous space algorithm, which is telling me xt. And I maintain in parallel a discrete space state rho t. Now I move in continuous space to xt plus 1, and I get this movement cost, W1. So what I'm going to do is, I have now xt, I have xt plus 1. So I can build the infimal coupling, right, the best coupling here. And I have my rho t. So now I'm just going to sample rho t plus 1 from this best coupling. Okay, so in expectation, my distance for the integral algorithm is going to be equal to my distance in the continuous space algorithm. Okay, so just like here, we had some argument to go from continuous time to discrete time. Here we have an argument to go from continuous space to discrete space. Okay, so we get to the following problem. So finally, and let me assume the following. Assuming that W1 for my metric space can be viewed between P and Q, can be viewed as some norm between P and Q. Okay? I'm going to assume that I have a certain form like this. I'm going to explain in more details in concrete examples what I mean. So let's assume for the moment, it's going to simplify my notation, that the Wasserstein distance between two probability distribution is just a norm between those two vectors. then I have two things. I have a service cost in continuous time, which is just the integral over time of the inner product between Ct and x of t dt. Right? That is exactly if rho t is distributed from xt, then this is my expected service cost. And my movement cost is going to be the integral of, the instantaneous Wasserstein distance, which is just the time derivative of x, the norm of the time derivative of x. So this is the integral of the norm of d over dt of x of t dt. Okay, so these are the two objects that we're going to look at. We have transferred the whole problem to looking at a service cost, which is an integral of xt inner product with ct, and the movement cost, which is the integral of the norm of the time derivative of xt. And xt is a point in the simplex that we're going to move in continuous time. And of course, what is it going to be? Xt is going to move according to the mirror descent flow on this cost function with a mirror map, which is going to be adapted for this norm. That's what's going to happen. Yes?
So in discrete time, Ct was the cost function.
Yes?
So now it's become just a vector in
Yeah, sure. I will keep doing that. If x is of size n, then I view C from x to R plus. It's the same thing as C, which is in R plus n. Right, so yeah. Okay, any other question? Okay, so let's do it. So the mirror descent flow. Maybe first, what is the maybe the mirror descent flow. Mirror descent flow on K, which is a simplex. Okay, I like to keep this general convex body because for more general metric spaces, we're going to have a more complicated state space than just the simplex. I will explain when we get there. So the mirror descent flow on K is just that the time derivative of xt is equal to minus the Hn of phi. Phi is this convex function that we design, inverse, applied to the cost function, plus lambda t. And lambda t is in the normal cone. Lambda t is in the normal cone of k at xt. And xt is restricted to be in k. Okay, and we said that there is a uniqueness and existence of the solution under those under mild condition on phi and c, which are verified here. Okay, so this, just to be clear, right now I have written an algorithm. You design a phi, and you do this water filling business. This gives you, you see in discrete time cost functions. You do this water filling business. This gives you a continuous time cost function to which you apply this equation. This gives you a continuous time evolution of the probability distribution, which in turn, through those infimal couplings, gives you a discrete time evolution of a discrete state space. Okay, a discrete state, sorry. But we can forget about all of this and just look at this equation and trying to analyze those two quantities. That's all we want to do. Yeah?
Just to understand the water filling.
Yes.
So this picture are the states.
Yes?
And you do this on the time one. At time one you have filled everything.
Yes, exactly. Yeah, that's right. Absolutely. But yeah, of course, time one doesn't necessarily mean anything. You can also go at rate one. I mean, whatever. Yeah. Yes?
Time t plus 1, you then say Ct plus 1 and then you fill it.
Exactly, yeah. Every time step you get a new CT, you fill it, you get a new one, you fill it.
And it doesn't depend on the rate.
It doesn't depend. I mean, you need to show that, no, it doesn't depend. Doesn't depend. Yes? No.
how do you sample from the distributions? You have an inverting distribution in the simplex.
Yes.
So at which time points do you decide to resample?
Yes, very good. So you do this infimal coupling. So it's hard to think about both continuous space and continuous time at the same time, but certainly the continuous space alone should be clear. If I move, in discrete time step, so if I move in discrete time step in continuous space, so this is my simplex. It doesn't really look like a simplex, but it's fine. And I'm here, and then I move to here. Then what I do is that I look at those 2 points. I look at the best coupling for them. Now, in parallel, I maintain my discrete state. And so I was in a state which was distributed according to this guy. Now I want a new state distributed according to this. So I'm doing kind of a filtering. Make sense? Yeah.
So for a given time point, discrete time,
Yes.
you keep a distribution rather than a fixed state.
I keep both. I keep the distribution and the state. So for instance, imagine, like the simplest thing to think about is, imagine that xt doesn't move. It's the same distribution again. I certainly shouldn't resample. And the informal coupling is going to tell me, don't resample. Keep it, and you're still correctly distributed. Right?
These weights are like the weights we saw yesterday in the lecture.
Which that?
The distribution we keep is like the multiplicative weights.
It's like the multiplicative weights, absolutely. Yes. Yes, exactly. Yeah. And we're going to see multiplicative weights. I mean, looks like we're not going to see it this hour, but we're going to see it. Okay, good. So remember, so miracle 1 was the mere fact that it's crazy that, these cities, they don't have to come from a fixed convex function. They can change over time, and, everything still works. Miracle 2 was the following calculation. Miracle 2 was the fact that the time derivative of the Bregman divergence between any fixed point y and this continuous time process is upper bounded by the inner product of ct with y minus xt. Remember this calculation? This was Miracle 2. This was the star of the second lecture, this calculation. Very, very simple, just a line. But it says something very deep, which is y is some fixed distribution. And if I regret not being at position y, if opt is at position y, and I regret because I'm not at position y, meaning that my cost right now is big compared to y, then this is decreasing. Okay, I get closer to y. So if there was a point which was better than me, then I get closer to it. And this was great, although we didn't see it, but for prediction with expert advice, this is exactly what you want because you compare yourself to a fixed point, to the fixed, the best in hindsight. But now in those problems, you cannot apply just this because you don't want to compare to a fixed y, you want to compare to a path. You want to compare to the optimal algorithm for the sequence, which might move all the time. So now you need to do a second calculation, which is Miracle 3. And this, in a sense, is really a miracle because mirror descent was not designed for that. Mirror descent, Nemirovsky has this calculation in his book, but he doesn't have the next one, which is equally simple. But so now what do we need to do? We need to look at what happens when y is moving. Okay, so let's say we keep ourselves fixed, but y is moving. Okay, so we want to say, if opt is staying in place, then we learn about it and we get closer to it. But from time to time, opt is going to move also. And what we want to make sure is that if he moves, of course, the Bregman is going to go up. But we want opt to pay for it. We want that if opt wants to become unpredictable, if opt wants to be, move somewhere and we lose track of him, he has to actually move in the metric space. Okay, so the question is, can we show that this is bounded by some movement of yt, which is the norm of the time derivative, I'm going to put dots now, of yt, right? This is the movement cost of opt. So what we want is to make sure that if this goes up, we lose sight of opt, then he paid for it. And if we have those two identities, then it's simple thing to show that we're going to be competitive up to the movement cost. I will explain that. So let's just do this calculation. So you remember the Bregman divergence is just phi of y minus phi of x minus grad phi of x inner product with y minus x. So when I differentiate with respect to y, I get the grad phi of y inner product with y dot here, and here I get the grad phi of x inner product with y dot. So I get that this is equal to grad phi of y of t inner product with minus grad phi of x, and this is inner product with y dot, the time derivative of y. And this is just by differentiating this thing. And I want to relate this to the norm of y dot, so I can just apply Hölder's inequality. So this is going to be bounded by the dual norm, so the norm dual to this thing, applied to this vector, times the primal norm of this. What is the dual norm of the gradient? You can really interpret it as the Lipschitz constant of the mirror map. So I'm going to call it L. So this is bounded by 2L times the norm of y dot. Okay, where L is the supremum over z in k of the dual norm of the gradient of phi at z. Okay, so this is the first time so far that a property of the mirror map appears in my argument. Right? Here we see we get some guidance toward what would be a good mirror map. A good mirror map is one which is Lipschitz in the appropriate norm, okay, whose derivative has a small gradient in the dual norm, where this norm represents the Wasserstein 1 distance. Okay, so let me put together those two identities into a lemma. So if I put them together, what do I get? So we get that the time derivative when both opt and alg are moving, this is upper bounded by the difference between the service cost of opt and alg plus the movement cost of opt, 2L times the norm of y dot of t. Okay, so if I just integrate over time this thing, what will I get? I will get something, some constant here, and here I will get the service cost of opt. Oh, and yeah, I always forget this. Let me put learning rates. This will make my life simpler. So you remember there is a learning rate here, eta. So I get an eta here. Okay, so I get eta here. Okay, I just get a learning rate. And the point I do that is for the following reason. So now if I integrate, so integrate, and what do you get? Okay, so here you get the Bregman divergence at the end minus the Bregman divergence at the beginning. Okay, so d phi at y capital T x of capital T minus d phi at time 0, 0. Okay, notice that this term is non-negative, and it's very natural to assume that alg and opt start at the same place, so this would be 0. So this term is non-negative. So this is non-negative if x naught equals y naught. And what do we get on the right-hand side? We get eta times the service cost of opt minus the service cost of alg plus 2L times the movement cost of opt. So let me just rewrite this, rearrange. So lemma. Take eta equals 2L. Okay, so your learning rate is twice the Lipschitz constant. Assume x naught equals y naught. You start at the same place, which is a very natural assumption. And if you don't have this assumption, it's just an added constant. Then the service cost of the algorithm is bounded by 1 times opt. Okay? So mirror descent automatically gives you a 1 competitive algorithm for the service cost. Okay? Of course, it is extremely easy to get a 1 competitive service cost algorithm. Do you have any suggestion for a 1 competitive service cost algorithm? Say in discrete time, discrete space. You can just always move to the cost to the state with the smallest cost. Just always move to the cost with to the state with smallest cost. Nobody can do better than that in terms of service cost. This is just the best. But maybe it moves a lot. So while this is great and I'm very happy with it, it also says nothing. Absolutely nothing by itself. The whole point is going to be about what about the movement cost of the algorithm. Okay, and this is where we hope that mirror descent does a very good trade-off between movement and service. But we already know, thanks to this lemma, we can forget about the service cost. Now, why is this still a nice lemma? It's a nice lemma because the whole difficulty of online algorithm and why people were stuck for a long time is that it's very hard to reason about opt. You have no information about what opt is doing. What this lemma allows you to do is that it allows you to completely forget about opt and use the service cost of the algorithm as a proxy for opt. So if you show, for instance, that the movement cost of the algorithm is bounded by the service cost of the algorithm, you're done, because you know that in turn this is bounded by opt. So now we can completely forget about opt, and it's just a self-reasoning argument about mirror descent. And you can see movement being related to service cost. It's like x dot equals x. So you can see the exponential coming up and the entropy and all of that, and that will be for the next hour. Is there any question before the coffee break? Yeah.
Yeah, this differential inclusion you have for the gradient flow.
Yes.
Is lambda part of the solution, or is it?
Absolutely, yes.
Okay, thank you. That was all.
Yeah. Yes.
Can you repeat how you choose
Yeah, I didn't explain. I mean, and that tells you that this cannot say anything interesting. This is true for any phi. Phi didn't appear at all. But that's also the beauty on the other end is that for any phi, the service cost is controlled. So now it's all pushed into the movement cost analysis. And in the movement cost, we're going to see that the properties of phi matter, and then we're going to select an honest, good-looking phi, which is going to be the entropy, for instance. Yeah, I could. So far, I could use maybe phi is the Euclidean norm, but you can already get a feel like this Wasserstein distance is going to be like an L1 norm. So if you use phi, which is like a Euclidean norm, you can expect that this Lipschitz constant is going to be dimension dependent, which is n, and we're shooting for log n. So we're going to have exactly the same issue as gradient descent for prediction with expert advice gives you an n, but if you use the entropy, you get a log n. So it's the exact same thing we'll have here. Yeah?
I'm still confused about going back to
Yes?
the original problem. So you said that you will take the state that's been visited that has the smallest cost in the initial description.
Yes?
And I still don't quite see how you do the same when you're manipulating solutions instead.
Yeah. Yeah, so I think the main confusion is that I did the two reduction like sequentially. So now you need to take both of them together. Yeah, I'm not sure I can do that in 1 second. So, but maybe I can do it with you just at the break. Yeah. Okay, thanks.